Geotrig day 3 of, no, day 2? Day 2 of lesson 3. So today we're going to talk about similar polygons as our start. Yesterday we talked about, what did we talk about yesterday? Triangles. We talked about the Pythagorean theorem and determining if we have right triangles, obtuse triangles, or acute triangles. And it all depends on if the hypotenuse squared is bigger than, equal to, or less than the sum of the squares of sides. So today we're going to take a different approach, and we're going to talk about similar polygons. So blank is a simple closed coplanar, all on the same plane, geometric figures whose sides are straight lines. Hence, it's all over the page and part of the initial naming of the slide. What is this?
Similar polygons.
It's going to just be polygons. So it's going to be, whoops, that's the highlighter. Polygons are the simple closed shapes. Okay? Now, you guys have to be careful. What are polygons? That red figure in the page here, that is a polygon. A rectangle is a polygon. A triangle is a polygon. What's not a polygon? Circle. Because, why? It's closed. It seems pretty simple, doesn't it? But what's the thing that's lacking? Straight lines or straight sides. Okay? That's the difference between a circle not being a polygon and all of the others being polygons. You guys okay with that? So actually, sorry, these objects should be down there. Yeah? So everybody just kind of cut and paste those two objects into what are examples of polygons. And of course, we could come up with many others. Stop signs, right? They have a special name.
Octagon. Polygon.
That'd be an octagon. I know those are supposed to be all connected, but it was a little harder to draw that on here. So there's a couple other things. Guys, polygons are made up of two things. Those two things are vertices and sides. Sides are the things that are the... What's a side? The sides are the pieces that connect corners to corners, right? Those are sides. So, hence, that's a triangle. It has three sides. Vertices, on the other hand, are the actual corners, angles. They form angles in the inside. So it's the corners. So vertices, let me change that to, like, say, purple here. A vertice is the corners, right? So vertices are the corners. Sides connect from one vertice to another that are adjacent to each other. Be careful with that. Can you guys see that I'm not connecting? Okay, I am not connecting those two vertices together. First of all, I missed like one of them, but those two vertices are not being connected. It's the ones adjacent. Adjacent means next to. Okay, not across the room, not across the polygon. So here's a really cool thing. Look at each one of our objects, the square, the triangle or rectangle, the triangle, the octagon. How many vertices are in the rectangle? How many vertices do you see here?
Four.
How many sides do you see?
Four.
So the number of vertices is the same as the number of sides. They match. So every time you have a vertice, you have a side. Cool? I think it's cool. Okay, so I took a photo of the book and I inserted it here. You don't necessarily need to write all of this down. Some of this you know. Okay, so remember all the angles of a polygon have equal measure and all the sides have equal length. If that's true, that's what we call a regular polygon. Right here. Regular polygon. Guys, this is what I call a regular pentagon or a regular polygon. Everything is the same. It's like if I ask you to draw a triangle, if I told everyone right now, take out a blank piece of paper and to make a triangle, I would assume, or a rectangle or a stop sign or an octagon, right? Most of us would draw a regular polygon. Because in our minds, this is, for a lack of better words, or maybe the right words, I'm not sure, this is like the most beautiful pentagon that we can make. I don't know if that kind of makes sense to you. An octagon. The most ideal octagon that you can think of is the typical stop sign. Everything is the same. So we say that's a regular polygon. So obviously, if it's regular when it's all the same, that means it is irregular when it's not. There's something satisfying about this seven-sided object, which almost probably would never even think of drawing. I don't know if I could even draw this by hand. This is done mathematically on a computer. You can obviously see this. But that means all the sides of these seven pieces are the same. And every angle, this obtuse angle, is the same. There's something appealing about that versus this. Right? Things can be symmetrical. Things look the same. All of those things are what we kind of, even human-like nature, thinks of beauty. Things that are symmetric. Things that are the same. Another takeaway from this slide. We have names for polygons. Up to a certain point, the mathematicians got lazy. We have to start with the smallest amount of sides and vertices that make a closed shape. And that happens to be 3. If you can draw a polygon with less than 3 sides, I would like to see it. But remember, they have to be straight lines. And it has to be closed. So it has to be a triangle. So, 3 sides are triangles. 4 sides are called quadrilateral. 5 sides are a pentagon. 6 sides is a hexagon. 7 sides is a heptagon. Octagon. 9 is nonagon. 10 is decagon. 11 is an ondecagon. Wow. And then 12 is a fun one, dodecagon. So, these are the common ones. Then after 12, they're like, this is starting to get ridiculous, that of me trying to come up with names for these things that everybody will accept. And so, once I get to 13, 14, 15, and on, I start to say, it's a 20-agon. It's a 25-agon. Now, could it be wrong in a long sense that I said it's a 5-agon? Not necessarily, but I think it'd be, for all of us, a pentagon would be easier to say. Okay? So, it's not important to memorize these. I think we know through the first 8. Maybe 7's a little wishy-washy for us, but the rest of them should be there. Okay? And the final, guys, the final things I want to talk about. Remember, if it's a dodecagon, it's got 12 sides and 12 vertices. Okay? That's number 1. Number 2, we have things called consecutive sides or consecutive vertices. That's these things right here. Consecutive sides and consecutive vertices. Those are the same thing when I talked about the adjacent next to. Consecutive means in a row. So if I'm up here at this vertice right here, a consecutive vertice to this one would be either the top one next to it or the one below it. You can go either direction, but I have to go around the object. I'm not going crisscrossing back and forth, none of that. Going around clockwise or counterclockwise. Those, you get to the vertices and their sides. When I do make a connection between vertices, if I do this on that heptagon, that is what we call a diagonal. And then a diagonal is a line segment of non-consecutive vertices. You're joining two vertices that are not next to each other. So if we take a look at our heptagon, we could go straight across the top. I'd have to skip a vertice. Then I have non-consecutives. That's called a diagonal. Okay? Any questions with that? That's all I got for this slide. Next up, we're going to talk about special types of polygons. So not only do we talk about regular polygons where everything is the same, we could talk about irregular polygons where things are different. We can talk about concave and convex. I'm going to start with concave. That's the first one anyways. Concave. When I think of concave, I think of a cave. And a cave would be a what? Dark, okay? But a cave to me would be like a hole, maybe. Or something like an indentation into a side of a hill or something. Think of that when you think of concave. So concave is not regular. Concave is if I had a pentagon, is if someone took one of those vertices and pushed it in. That is still a pentagon. How many vertices do I have? I still have 5 vertices. I also still have 5 sides. But one of those vertices is pointing inward. Okay. You guys write this down, because I'm not going to write this down. There is a concavity test. So we're all going to take a test.
No.
The concavity test says that a polygon is concave if you go from one point to another point. So what I do is if I draw a straight line between 2 points inside of a polygon, and I have to leave the polygon before I go back in, it's concave. Someone pushed it in. Do you see that I had to leave the outside? I crossed the edges or the sides. That makes it concave. So on the flip side, if I can connect any 2 points on the inside and not cross to the outside, then it has to be, the second word, convex. That's also a pentagon. Would you guys agree?
Yeah.
It's not a regular pentagon. It doesn't have to be a regular pentagon. But look at this. If I decide to join 2 points, did I have to leave the outside? Or inside, sorry. No. Did I have to leave? 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 No. I can keep drawing as many lines as I want. But as soon as I find one piece of evidence that I have to leave the inside of a polynomial, I know that it's concave. Guys, in math, it's always easier to prove something wrong than it is to prove something correct. If I said that every time I drive my car, I use my turn signals.
It's like turn signals don't work.
Okay.
He uses his hands.
Anyways,
I have a flag.
if you guys wanted to prove me wrong, you guys would have to be the creepy student and follow Mr. Konchak. Yes? When could you eventually stop following me? If you were to prove me wrong.
Wait, repeat the story.
Why am I going to repeat the story? As soon as I turned and did not use my turn signals. It could be one block out of school on the very first day, or it might be 30 years down the road. My statement was I always use my turn signals. So all you have to do is find me doing it once, or not doing it, right? Proves me wrong. But how much work would it take to literally prove me correct?
I could follow.
You would have to follow every time I'm in a car and I use the turn signals. There it is. There it is. That's really hard. Mathematics is the same way. To prove something is true, you have to be able to back up and prove it under all conditions. But to prove something wrong, you just need to come up with one example that disproves it, you're done. So that's the same thing here. In the concave problem, I found one example where I had to leave the inside, go to the outside before I came back in. That's concave. It doesn't matter if it's really far or it's really close or not very far. So if I wanted, I could have done this. I don't know if you guys can even see that. You see that right there? I crossed just to the outside, just a little bit right there. Guess what? It's concave. You guys get that?
Because it went outside.
Because it went outside. Similar. Here's a different one. Similar means. Does anybody have a definition for similar? What does it mean to be similar?
Alike.
Alike. Okay, well, I'll put alike. It's alike. Does it mean they have to be the same?
No, because they're similar.
So, one inevitable fact for most of us, or a lot of us, is the fact that we are going to be looking similar to our parents. Okay? It's kind of interesting when it comes to conference times. There are times where you're like, it's undeniably, I know which kid is yours, you don't have to speak. And other times I'm like, okay, you're going to have to help me out here. But similar means alike. It does not mean the same. So, a little bit more formal definition when we talk about polygons. So it has the same angles, but different size. Okay? It has to have the same angles, because that's what makes it look the same, or similar, sorry. To make it look the similar, the proportion of angles and things have to be the same. But it has to have a different size, and then underneath this, I'm going to put it in a different color because it's kind of important, aka similar ratio. Now, what does that mean? That means it has to be proportional. It means that if I have two objects, okay, look at this. That we're going to call is a square. It will be similar to this square. Granted, they're supposed to be squares. Do they have the same angles? All squares have what for angles? 90s. What it means to be similar is that all of our angles will be the same. Okay, they're all 90s. But if this is a side length of 1 and this is 2, they have a ratio of 1 to 2. Or, going from the larger to the smaller, 2 to 1. But because these are squares, it has to be consistent. It has to have a similar ratio, which means every corresponding side will have a similar ratio to the other corresponding sides. Do you guys get this? So if I, again, drew a pentagon and I said these two objects were similar, all of my angles between these have to be the same in their corresponding positions. But then this side and this side will have a common ratio. It could be 3 to 5. It could be 5 to 20. Or 5 to 21. But whatever that ratio is between these two sides will be the same for all of the other sides. If you think about being similar, it means exactly the same but smaller or larger. It's a dilation or an enlargement. It's like me taking a drawing, like one of these, going to a photo machine and hitting the enlarge button. Zip, bigger. Right? Or make it smaller. Does that kind of make sense?
Yeah.
Everything about it is exactly the same proportions. It's just larger or smaller. Okay? Any questions on that? And that is, okay, let me go back here. What I put here for similar ratio is what I want to say here. Your scale factor is a similar ratio. So when I talked about 1 to 2 or 3 to 5, that is the scale factor. The scale factor is what is the difference between similar objects. We will be dealing a lot with similar triangles. Okay? Equal or congruent angles, similar or a ratio scale factor between sides. Now, I just kind of filled this in. For two polygons to be similar, the measures of blank angles must be equal. What's that word? I used it a couple times. What is it? Starts with a C. Corresponding. So, corresponding angles must be equal. The length of corresponding sides must be similar. Did we say similar? We could say similar. It's part of that. I would say maybe even back this up and say the lengths of the sides must be with a common ratio instead. Maybe that might be a little bit more rememberable. Is that the right word? To be able to remember that. So it has to have a common ratio, aka scale factor. Okay, so the book's going to use scale factor. I'm going to use scale factor or common ratio. Those two things are going to come into play. So the last part, putting this all together, is similar triangles. So the definition, they have one there. Similar triangles have the same angles, but have a common ratio or a scale factor. And so, what we have to look here, and as you can read, when two angles in one triangle have the same measure of two angles in another triangle, the triangles are similar because the remaining angle has to be the same. So, what I'm trying to get at here, because we know all of the angles in a triangle add up to what magical number?
180.
180. If you know two of them in any particular triangle, you can find the third angle, right?
Yes.
So if one was 60, the other one was 40, that adds up to 100. The remaining one is 80. So, on the same premise, if I say, now, if we said that angle B and angle E are the same, we would put tick marks there, right? Because that would denote to everyone that we know those two angles are the same. And if by chance we went up to A and said A was congruent to angle D, the only logical, or the next logical step would be that if you knew that these two angles were exactly the same, these two are the same, those two are the same, it's only logical that the third angle also has to be the same. So, therefore, I can put a band of 3 on there. If you guys don't want to use 3 bands, you could use a single band with its own tick mark. As in, you could do this. Okay? That changes up your tick marks so you guys can see those. Now, why is this important? Why did you just show me this? That 2 angles leads to all 3 angles. Because as soon as I can claim that 3 angles in a triangle are congruent to another 3 angles, I can then claim that the 2 triangles are similar. And if they are similar, triangles are kind of unique. Because once I state that the angles are the same, they're similar, that means I can find their side ratios. You're going to need vertical angles, sometimes alternate exterior, alternate interior for parallel lines. All of those things are going to come into play. So, we have an example below. These 2 triangles are joined or made from 2 intersecting lines. We have sides x, 4, and 5, 6, 7, and y. It wants us to find x and y. Notice they already filled some information in for us. They said the 2 angles in the middle are the same. By what definition? I've already said it today.
Interior.
No, not interior.
I was looking at the angle.
It starts with a V.
No, vertical.
They're vertical angles. These are vertical angles. Now this is given to us. So, but those ones you could figure out on your own. The 2 other angles way up here on these sides, they're just given to us. At this point, I cannot claim alternate interior or exterior because I really do not know if these 2 lines are parallel. If they were parallel, then absolutely they're alternate interior. But this was given. These are givens. These 2 angles are congruent to those 2 angles. So what happens about these angles? By definition, they have to be the same, and so they are congruent. You now showed, number 1, guys, to use triangle congruency, number 1, you need to show the triangles are similar. To show similarity, you need to show all the angles are the same. Once you've established this, we now can look for corresponding sides and look for the ratio, aka scale factor. So, How do I do this? I use the tick marks. I say, look at this. This is my single tick mark right here, right? Single tick mark in this triangle is associated with this side opposite of 4. 4 is similar to what? To y. So 4 is to y as, let's find a different angle. Let's do this red one, the double band. 5 is to, opposite the double is 7, which will equal, guys, the double banded, or the double tick mark of x over 6. All 3 of those ratios need to be the same. They have to have a common ratio, or aka scale factor. Is any one of those completely filled in for us?
Yeah, 5 over 7.
5 over 7. Which means, guys, left side is on the top, and the right side is on the bottom. So we are doing left over right. So that means the right side is slightly larger than the left. Can you guys see that ratio happening? Because 5 to 7. Now, if I wanted to solve these, I cannot solve all 3 together at once. I need to cut it and say just those 2 are equal. So, when does 4 over y equal 5 over 7? What do we have to do to solve that? Cross multiply. So, cross multiply becomes 5y equals 4 times 7? 28. And then I'll divide by 5. So y is equal to 28 over 5. I don't think I can reduce that. Great. I found y. To find x, I have just take the same ratios and break it up differently. I'll use these 2 instead. So when does 5 over 7 equal x over 6? To solve it, I'm going to cross multiply. 30 equals 7x. Divide by 7. X equals 30 over 7. I think, again, I can't do anything with it. And therefore, you found x and y.
Good job,
So, guys, there are 3 more examples that we will do, but this is the homework for the rest of lesson 3. 3, 7 through 10, 13, 15, and 28. The 3 other examples will help you with the 7 through 10. So that's what we'll do next time. There won't be a video for that. So stop in and ask questions, but everybody will have the assignments. Have a great day.